Hello once again, AP Calculus AP students, Mr. Record here, and we're kind of continuing our first video on the chain rule. This would be my chain rule part 2 video, and it really does focus here on this shortcut that we briefly mentioned in the last video. The shortcut really has a specific name. It's called the general power rule. It's okay to call it the shortcut for the chain rule, but sometimes it's kind of important to express things in a more formal manner. And this particular rule is kind of built upon us understanding that a typical function will have this form. You'll have a y equal a u
nth power.
The last video is the inner function, and this something to the nth power. This nth power is kind of like your outer function. And the short way to really take this derivative is just to apply your old power rule shortcut, but then tack on this little chain rule piece. So you'll see here that we allow that exponent, this n exponent, to pop out in front right here. Keep the u of x just the way it was. Don't change a thing about it. But then lower that exponent by 1. And then here's the chain rule part right here. You would multiply by du over dx, which is essentially just the derivative of what this inner piece was. Now, the equivalent expression down here below is really exactly the same thing. All I've done is just eliminated the of x, the parenthesis x, and took away the du dx notation, or at least replaced it with prime notation. And it's just sometimes it's a little easier to look at. All right, so what I'm going to do in this next example 3 is simply take each of these and try to apply this shortcut. There's nothing wrong if a student wanted to write out the u equal expression. This is very similar to what I did in the last video. You may not want to write this out, but you could write this, and then you could add the y equal expression, which in this case would be y equal u cubed, and then of course you would multiply the two derivatives of these two pieces together, and then write your answer in terms of x. But I think what an easier way is to go ahead and apply this shortcut that we just spoke of. So in this particular case, example 3a, we are going to take the exponent 3 and immediately pop that out in front. Okay, and then the 3x minus 2x squared, we don't change anything about it. 3x minus 2x squared will stay in those parentheses. Now the exponent, remember, was a 3. We lessen it by 1 so we make it squared, and then we don't stop here. You haven't completed the chain rule yet. Now we would multiply by what is inside of the parentheses, the derivative, I should say, of what is inside the parentheses. And that would be 3 minus 4x. And there's nothing wrong with leaving the derivative just like this. It really doesn't simplify. You could rearrange these two binomials, but that's not important whatsoever. Let's take a look at b. Again, we can apply the chain rule shortcut here. But what I'm going to suggest that we do first is to get out of this radical notation. We've always said that radicals don't really behave nicely when we're trying to take derivatives, and we always rewrite them. This is no different. We just got to make sure that we write the correct exponent. If we have the cube root of something squared, we have to think, is that a 3/2? Is that a 2/3? Which order does it go in? And if you recall, the exponent is always going to be the numerator. The index will be the denominator. So you have what's a 2/3 power here. All right, now at this point we can go ahead, take our derivative by using the general power rule. The 2/3 exponent will come right out in front, multiply by the x squared minus 1 to a power less than 2/3. 2/3 minus 1. We have to think 2/3 minus 1. That's what's going to go in this spot. 2/3 minus 1 is indeed negative 1/3. And then we finish up by multiplying by the derivative of what is inside of the parentheses, which is 2x. Okay? Now, we do have a little bit of simplifying that we could do here, and I think we should take care of it. A couple of things. First of all, the 2/3 and the 2x could sort of multiply together a little bit, and you would have a 4x on top, and the 3 would be on bottom. In fact, I probably didn't plan this very well. Let's see if I can do a little rearrange. Perfect, perfect. I can see that I'm going to not need any more terms there in the numerator. And then this x squared minus 1, this x squared minus 1 to the negative 1/3, because he is indeed raised to a negative exponent, that means he can go down into the denominator alongside the 3. And quite honestly, that doesn't really matter to me, and most calculus teachers would probably agree. You could either write it back with a radical form like this, or you could keep it with a 1/3 fractional exponent form, and that would be just as fine. So anyhow, that would be your final simplified answer to example 3b. And then finally, let's look at 3c, very similar kind of problem. Again, I think it's in our best interest to rewrite this first of all so that it's in that nice form. The -7 coefficient will just carry straight down, and as you can imagine, the 2x minus 3 would be raised to the -2 power. All right, so we have dy dx being taken. We do use the general power rule, so we multiply the -2 and the -7. That would give us a positive 14. 2x minus 3 is now going to be raised to the 1 less than -2. Sometimes you have to be careful when you're in the negative number world. When you subtract, the numbers actually look like they get bigger in size, but because they're negative, they really are getting smaller. So our exponent is -3. And then are we finished? No, we have to take the derivative of 2x minus 3, which of course is 2. Now once again, this can be simplified just a tad. We've got a 14 times a 2 that can multiply. That would make 28. And then the 2x minus 3, because it has a -3 exponent, it is best that it is written down in the denominator, now with a positive 3 exponent. And there you go. You've got example 3a, b, and c that you can look at now and sort of pattern some of the future problems off of them. But really the chain rule, the general power rule, is quite easy, and it's just one of those things, like many things in calculus. The more you practice it, the better you're going to get. Anyway, I hope this helps, and I'll see you next time.